everyone, welcome back to my channel Ankura Education. Our today's topic is about the electron gas theory. According to the electron gas theory, the electrons are in continuous motion and the direction of path or the flight will change when they collide with the ions. That means the direction of electrons will be changed when they collide with the ions in the metal. That means other ions in the metal. So the average distance between such collisions is called as the mean free path. Now let us consider that an applied field epsilon, electric field epsilon is applied to a metal, which is in volts per meter is applied to a metal. So due to the electrostatic force, the electrons would accelerate, but that means they move with infinite speed until they collide with some ion. But the electron collides with number of ions and they lose their energy. Due to the loss of this energy, the velocity of the electron decreases. This decrease in velocity is called as the drift velocity. The direction of this velocity is opposite to the direction of electric field, applied electric field, and its magnitude is proportional to the electric field. So we get V proportional to epsilon. So if we want to remove this proportional, then we have to add a proportionality constant. So we get V is equal to mu epsilon, where mu is the mobility. So we can define the drift velocity as the velocity possessed by the electrons under the influence of applied electric field. So this is the final equation for the drift velocity V, which is equal to mu into epsilon. So the drift velocity depends upon the electric field and the mobility of the electrons. If a graph is plotted between the applied electric field epsilon on x-axis and drift velocity v on y-axis, then it would be like this, as shown in this figure. The drift velocity increases initially and then it reaches to a steady state after some time. This is as shown in the figure. This mu is an important parameter in this concept, that is the mobility. So from the equation V is equal to mu epsilon, we can write mu is equal to V by epsilon, where the units for V are in meters per second and epsilon units are volts per meter. Hence we can say the units of mu as meter square per volt second or centimeter square per volt second. So as the temperature increases, the mobility decreases. This is explained by using a relation mu proportional to t to the power of minus m or mu proportional to 1 by t power m. This is the expression for the mobility in case of an atom. So where m is the constant, and this constant for silicon, it is 2.5 for electrons and 2.7 for holes. So this value will be different for holes and electrons. The constant value will be different for electrons and holes. When compared to silicon, the germanium has its values as 1.66 for electrons and 2.33 for holes. So there are different values for silicon and germanium for this constant. If a graph is plotted between the mu on y-axis and t on x-axis in log scale, we get it as shown in the figure. And the value of mobility depends upon the type of scattering. There are two types of scatterings. One is the lattice scattering and another one is the impurity scattering. This lattice scattering mobility is denoted by mu L and the impurity scattering mobility is denoted by mu I. The mobility decreases due to the scattering. And from this graph we can say that the lattice mobility is proportional to t to the power of 3 by 4 and the impurity mobility is proportional to t to the power of 3 by 2. So we can say that 1 by mu is equal to 1 by mu L plus 1 by mu I. That is the total mobility is the sum of the lattice and the impurity mobilities. And we can generalize this mobility equation as 1 by mu is equal to 1 by mu 1 plus 1 by mu 2 plus 1 by mu 3 plus and so on. This is a generalized expression for the mobility. This is very useful in solving the problems as well as in GATE exam. And the mobility depends upon the applied electric field. So mu is a constant for values of applied field less than 10 to the power of 3 volts per meter, and mu proportional to epsilon power minus half or 1 by root epsilon for 10 to the power of 3 less than epsilon less than 10 to the power of 4 volts per meter, and mu is proportional to epsilon power minus half minus 1, that is epsilon inverse, or 1 by epsilon for epsilon greater than 10 to the power of 4 volts per meter. moles per meter. These three conditions shows the relation of mu and epsilon. How mu depends upon the applied electric field, that is the mobility depends upon the applied electric field. If we have mu n, then we can say this as mobility of electrons, and if we have mu p, then we can say that mobility of holes. These semiconductors, silicon and germanium, we have these values as mu n is equal to 1300 centimeters square per volt second, or if we convert it into meters, we get 0.13 meters per volt second, and mu p is equal to 500 centimeters square per volt second, that is equal to 0.05 meters square per volt second. For germanium, we have mu n is equal to 3800 centimeters square per volt second, that is equal to 0.38 meters square per volt second, and mu p is equal to 1800 centimeters square per volt second, that is equal to 0.18 meters square per volt second. So here the mobility of the electrons is more when compared to holes. Not only here, in any kind of atom, the mobility of electrons is more when compared to mobility of holes, because the protons are attracted towards the nucleus than electrons, and the electrons move with a higher speed. So the mobility of the electrons is more when compared to mobility of electrons. High frequency and radio frequency applications uses gallium arsenide than silicon, because the gallium arsenide has the mobility of electrons as 8500 centimeters square per volt second, and mobility of holes has 400 centimeters square per volt second. Since the mobility of electrons in gallium arsenide is more when compared to silicon, this is preferred in high frequency and radio frequency applications. Frequency of the electronic devices depends upon the mobility, and the mu n is greater than mu p. This is discussed earlier. So now let us consider a metal n with length L and time t. T is the time taken for the electrons to travel from one end to the other end. That means it is the time taken for the electrons to travel from one end to the other end. So let us denote it as T, and A is the area. So we have the drift velocity V is equal to L by T. Let us consider this as equation number 1, and the current I is equal to total charge by time. So charge is equal to N into Q by T, where capital N is the number of electrons and Q is the charge of electron, where capital Q is the total charge. So the current density J is equal to current per unit area, so I by A. That implies J is equal to, if we substitute I, we get NQ by T into A. Let us consider this as equation number 2. From these equations 1 and 2, we have J is equal to NQ by T, means L by V into A. So that is equal to NQV by L into A. And we know that N by La is equal to small n, which is the electron concentration. That means capital N is the number of electrons. Number of electrons per volume is called as the electron concentration, that is denoted by small n. So we can replace this as J is equal to NQV. And we know that V is equal to mu into epsilon. So J is equal to NQ, in place of V we are writing mu epsilon. So J is equal to NQ mu epsilon. So the current density J is equal to NQ mu epsilon. And from Ohm's law we have J is equal to sigma epsilon, where sigma is the conductivity of the material. So I will write it here neatly. From Ohm's law we have J is equal to sigma epsilon. So by comparing this equation with the above equation, we get sigma is equal to NQ mu epsilon. That is, with the above expression means NQ mu epsilon, we are getting sigma is equal to NQ mu. This is the conductivity of the material, and its units are in ohms per meter, mhos per meter. Mho means it's a ohm inverse. This we have already know. This is a basic concept. And the units of conductivity are also expressed in Siemens per meter or Siemens per centimeter. And the resistivity, which is the inverse of the conductivity, that is resistivity is equal to 1 by sigma is equal to 1 by NQ mu, whose units are in ohm per ohm centimeter or ohms meter. So we can write the expression for resistivity as 1 by n cube mu from the conductivity expression, and J is equal to n mu q epsilon, and its units are in ampere per centimeter square or ampere per meter square. These units are very useful in solving the problems as well as in objective type questions in all kinds of competitive exam and GATE exam. And I is equal to, that is, the current is equal to current density into unit area. So I is equal to, we get it as n q mu epsilon A. So I hope you understand my concept, and that's it for today. Thank you for watching my video. If you like my video, please do like, share and subscribe to my channel. If you have any doubts and suggestions, please do comment in my comment box. Thank you.